What we're doing today, again, is a very important thing to understand about physics, how to know when you should apply momentum conservation, mechanical energy conservation, maybe both, maybe neither. So all the forces that we've learned about so far can be thought of in categories or groupings. Okay? For momentum, you're concerned if it's an internal force or an external force. Whether it's something that's happening within the system or something coming in from outside. As long as it's within the system, momentum conservation doesn't care. Momentum is conserved. So you notice that the internal here, momentum is conserved in both. Now there's another way to categorize forces, whether they fall into the conservative or non-conservative camps. Conservative forces are ones where they can store energy in terms of potential energy, and we call it potential energy because we can get it right back. So kinetic and potential energy are traded, but the total, which we call mechanical energy, is not changed. So on the conservative side, you can see mechanical energy is there. Okay, it's conserved. But there are other forces, like chemical, when you're doing an applied force, you can have chemical energy involved. Friction, you can take energy to thermal. Those are forces that we call non-conservative, and mechanical energy is not conservative. So, what I'm going to do here is go through a bunch of scenarios. I already kind of talked through one at the end of last lecture. Let me review. Here's my first scenario. We have a horizontal frictionless surface where we have a collision of two objects, and that's my system. Is momentum conserved? Yes, because that collision force is internal. Okay, so we've taken great pains to isolate that system from any external forces by making it horizontal and frictionless. So momentum conservation is happy because it's inside, but energy is a little more nosy. It wants to know, oh, okay, it's internal, but tell me what kind of internal. Okay? You could have an internal conservative force, in which case energy is conserved. What happens during such a collision? Well, kinetic energy gets transferred into potential energy, another kind of potential energy which we call spring potential energy, during the collision. So you can imagine that a spring compresses, absorbs energy, but then says, here you go, take it back. So the kinetic energy goes into potential energy of the spring during the collision, and then finally it comes back out here. So the initial and final kinetic energy of the system is conserved. So KE system initial equals KE system final. Okay? The kinetic energy is all there before and after the collision. So you count up the kinetic energies of the objects at the beginning and the kinetic energies at the end, you're going to get the same number. Okay? This is called an elastic collision. It's called elastic because it may not necessarily literally be a spring between them, but the objects could just be springy. In other words, what happens is that the objects compress, and you can imagine like two rubber balls colliding. They compress, but then they say, here, take that energy back. So they store it up during the collision, but then they return it to the objects afterwards. So that's the elastic collision. But it's also possible for that internal collision force to be non-conservative. Maybe two things collide like this, right? Then you're clearly sending some energy to heat. Okay? Maybe it's like a head-on car crash, right? Maybe the things compress, but then, of course, two cars don't kind of uncrumble again, right? The damage is permanent. The energy is not stored in the compression. That compression is permanent. In fact, that energy has gone to thermal in the environment. Okay? And so, that is a different way for an internal collision to proceed as non-conservative. During the collision, some of the kinetic energy of the system gets sent to thermal, and you're not getting it back. So you're going to have that the kinetic energy of the system initially is bigger, and at the end, it's not all going to be there. And we know where it went. It's not that we destroyed energy into nothing. It went to thermal. But we're not expecting to see it all there. This is called an inelastic collision. And I guess, by the way, I should say I've been talking about mechanical energy. But of course, if this is all happening on level ground, then potential energy of gravity is constant anyway. This is gravity. So really, when we talk about mechanical energy, we're talking about kinetic energy. Is the kinetic energy all there at the end? If it is, you have the elastic collision. If it's not, you have inelastic. Okay? You guys will get a chance to try both of these out in lab on this week. And it all just comes down to how you're going to manage that internal collision force. So what are the details of how that internal collision force happens? You'll have various different ways in which they interact. One is with a spring, and one is with Velcro, which is obviously highly frictiony. I should say, by the way, it's a rusty spring, so it's not going to give you all the energy back perfectly. So you might ask, is there a middle ground? We actually do have some shades of gray in the elastic and inelastic. I should mention that the inelastic is actually split up into two categories. There's the somewhat and completely inelastic. The completely inelastic is actually the end of the road. It's actually the most energy you could lose. You have maximum kinetic energy of the system loss. Now, how do you know if you've lost the maximum amount of kinetic energy you possibly can? You might say, well, does the system just stop? Well, it can't just stop because your momentum is still conserved. And remember that momentum often says that, for instance, if the system momentum is non-zero to begin with, it can't be zero at the end. It can't just stop dead because you would give up on your obligations to momentum conservation. So it's not just about stopping. What it is about is if a surface is completely elastic, it compresses and then uncompresses and gives all the energy back. It's possible, by the way, for it to compress, have some energy go to heat, but then still uncompress. But when they compress and don't spring back at all because you killed all the energy, none of it's going to get given back. When you compress, when all the energy goes into compression and goes into thermal, what it leaves is that these two objects are stuck together. Maybe not literally stuck together, but they're moving the same. Because if you compress and there's no uncompress, then the two objects are stuck together or kind of have the same velocity. So you know you have one of these when they have the objects have the same final velocity. Stick together. That's a dead giveaway. If you ever see a collision where the two go off together at the end, you know you have a completely inelastic collision. You know that you've lost kinetic energy in that collision. In fact, you've lost the most you could while still maintaining your obligations to momentum conservation. So the two things will stick together and have the bare minimum momentum that is necessary to maintain the momentum that came in. Question?
So if the final velocity is zero, does that count as an inelastic, completely elastic?
As long as they're moving together. So they could be both stopped, but they could both be just moving with the same common final velocity. The only way that they could both stop, that would also mean momentum is zero, so the momentum of the system would happen to have to be zero to start with, right? So that's not always true. So that's a dead giveaway. You know if two objects move together after the collision, you've lost kinetic energy. In fact, you've lost the most you can. Basically, think of it like this. The two objects don't even have enough energy left to bounce off, okay? They stay together. A somewhat inelastic collision is that some kinetic energy is returned to the objects after the collision, so they don't stick together. Okay? So they don't stick. So it can be hard to tell by sight whether you have the elastic or somewhat inelastic. The two objects do bounce, and it's unclear whether you lost some energy or no energy at all. There you have to go to the numbers. Okay? So common mistake, students either think it's elastic, where no energy is lost at all, or completely inelastic, where you've lost all of it. There is a middle category. Okay? So don't forget, if you see the two objects bounce off, don't necessarily assume that all the kinetic energy is there at the end. Some of it may have gone, not as much as it could have, so that they could have stuck together. Okay? So don't forget about the middle category, especially because somewhat inelastic is probably one of the more common types of collisions. So for instance, if you are on the highway, right? The two cars try to merge in the same lane, and they go like that. They bounce off each other. They don't stick together. The collision isn't as bad as it might have been, right? It's not head on. They don't end up in a jumble wreck together. But of course you lose some energy to the environment doing that, right? Both of their door panels are could be permanently crushed, right? That sent energy to thermal. You probably heard that collision, right? That's energy that went to the environment as a sound wave. You lost some energy. Not as much as you could have, but some. So it's very typical for things to have a collision, a little bit of energy to be lost to the environment, but most of it still being there at the end. Okay? So when you do your collision in lab this week with a rusty spring, okay, remember the spring is rusty. Okay, I'll tell you right now, what kind of collision is it? It's somewhat inelastic. You lose some energy to the environment because the spring is rusty, but the spring does manage to return some of the energy back to the objects, right? The elastic collision is kind of like a unicorn or a free lunch, okay? It's something that really is pretty rare, okay? Bordering on impossible to get, right? Because every collision, you lose a little bit of energy, right? Maybe it's minimal enough that you're willing to call it elastic, but every collision there's at least a little bit of energy lost, okay? Are there any questions on that? Okay, so you'll have a chance to try these out in lab this week. You'll have a chance to see how well is momentum conserved and how much energy is lost. Okay, hopefully, if you set this up carefully, you'll find that momentum is conserved. But depending on the nature of the internal collision, how exactly you do it, whether it's an internal conservative or non-conservative, you'll find the energy loss from within the system can be either minimal or extreme. Okay, any questions on those scenarios before I do some other ones? Okay, so let's do another scenario. I'm going to have two people pushing off each other on ice. So that's my system. So let's think through this. If I gave you this on the exam. Is momentum conserved for this two-person system? Remember, what you're thinking about is are there only internal forces, or is there a net external force? Is momentum conserved? Yes. And the reason why is because internal forces only. They push off each other, but that's inside the system. They're on a patch of ice, which is basically real-world speak for about as frictionless as you're going to get, right? So we have a horizontal and frictionless surface, so these guys are left alone by the outside environment. And here's a tricky one. Is the mechanical energy conserved? And by the way, since this is happening on a horizontal surface, we're really just talking about kinetic energy. So is the kinetic energy conserved? No. No? What happens to it? What? What is it? What happens to it? Yeah.
I didn't say anything, but I'm guessing it's lost.
Well, how much kinetic energy do they have when they're both just standing there? Zero. You can't lose any more. You don't have any to start with, right? Afterwards, they both have some.
Increasing.
It's increasing. Now, you might say, well, isn't one going to the left and one going to the right? Can't the kinetic energy still at a zero? Well, remember, kinetic energy is not a vector. You can't say that a leftward and a rightward one cancel. Before, neither of them have kinetic energy, and afterwards they both have some. So the kinetic energy actually increases. So the mechanical energy is not going to be conserved. We once again have an internal, non-conservative force. I guess to draw a distinction between that case and the last one, here the mechanical energy decreased, here it increases. Where does it come from? Where does the system suddenly get energy? Yeah?
Is it chemical energy?
That's right. Chemical energy from within. It's from within, so momentum conservation doesn't care. As long as it's internal, momentum's happy. But energy, we have that it's coming from chemical into kinetic, and so we see an increase. Before, neither of them have kinetic energy. Afterwards, they both have some, so we have energy coming from somewhere. So notice that within the system, something that happens within the system, it can either send energy away or have energy come in to mechanical. We can either send energy away from mechanical into thermal, as it happens in the inelastic collision, where we're expecting that the kinetic energy of the system initially is bigger and we lose it. But here we have energy coming in from within, right? So we have the energy from inside the system is being converted from another form, chemical, into the system. So here, we have the kinetic energy of the system initially is smaller than what we see at the end. Sometimes these are called explosions. Now obviously this is not an explosion, no one would call this an explosion, but that's another good way to get chemical energy into a system, is by having some kind of explosion that suddenly sends kinetic energy out into the system. So inelastic collisions and explosions are ways where from within the system can either send energy away or have energy come in. Okay? I guess we should catalog these guys. We have cases A, let's see, let me label them. So how do I want to label these? A, B, and C. A, B, C. Let's put them over here. We have A is the elastic collision that's over here, and we have B and C over here. Those are cases where the momentum is conserved, but due to the internal non-conservative force, the energy is not. It's either increased or decreased. Okay? So I'm purposely trying to show you these scenarios so that when you see them on an exam, you can evaluate which one you have. I'll try to do most permutations so none of them are really a surprise. Let's do another one. We'll do a ball falling through the air. So my system is just that ball. All right? Is momentum conserved for that ball? No. See a few heads. I mean, momentum is just mass times velocity, right? Mass is constant, but what's happened to the velocity? It's increasing. So what happens to the momentum? It's increasing. Okay, why is that? Gravity, right, which is an external force. So momentum conserved? No. There is an net external force to this system, which is really important. And that, in fact, is what changes the momentum. It's gravity. So gravity is external, but what kind of force is it? It's conservative or non-conservative? Conservative. So what does it do? It just trades kinetic and potential energy, right? Is the mechanical energy overall conserved? Yes. Yes, it is. We have that gravity will just trade between these two forms, but the sum is constant. This would be an external conservative force. So here we found momentum conservation is not very useful. Not that we knew about it at the time, but we found that energy conservation was, of course, the way to go. Your last homework was all about this kind of stuff, right? We hadn't introduced momentum yet because it's not even useful, okay? It's because gravity is an external force. Where does it come from, by the way? Where does the gravitational pull on the ball come from? Earth, yeah. So what we could do is we could turn this into a collision. We could turn it into a collision with the Earth, right? If it gets stuck in the mud, right, what kind of collision is it?
Inelastic.
Inelastic. And then specifically if it gets stuck in the mud, it's completely inelastic, right? So what we could do if we really wanted to, we could actually invite the thing that's the external force, which is the entire Earth, we can invite it into the system. That's one of the pieces of trickery you can sometimes apply. If you don't want to deal with an external force, invite whatever's causing it into your system. Now it's an internal force, right? So you could say that even though the momentum of the ball is not conserved, the momentum of the ball plus Earth system is conserved. So that's the beauty of momentum conservation, is that internal versus external is something that's up to you. It's this, who do you decide to invite in your club? Who's in your system? So what you try to do if you're using momentum conservation is you try to come up with a group of objects that are heavily interacting with each other and minimally interacting with the outside world. And then that's your collection that you're going to keep track of momentum conservation. You don't have that freedom, by the way, with energy, right? There's nothing you can do to convert a conservative force into a non-conservative force. Those are what they are. But internal versus external is a matter of perspective, right? If you don't like dealing with an external force, invite what's causing it into your system, make it an internal force. I don't know why we do that in this case. We probably want to just use energy conservation on this. But I'm just trying to point out that you could. You could turn a ball falling on Earth and getting stuck in the mud, and we could turn it into a collision by inviting the Earth into your system. Are there any questions on that before I do the last one? Okay, so my last scenario is an object sliding across a surface and it encounters a friction patch. Sliding, it's going to slide across some friction. Okay, is momentum going to be conserved for that box? No. In fact, the velocity is going to get decreased. So momentum is just mass times velocity, so the momentum is going to decrease. So why is it that the momentum is not conserved? It's force of friction. It's external, right? So there's a net external force that's important. It's the force of kinetic friction. So that again, for momentum conservation, you're trying to decide, is that force coming from outside or your system, or is it from within? In this case, it's from outside. Okay, how about, now we have to ask for energy conservation, is it conservative or non-conservative? So is friction conservative or non-conservative? Non-conservative. So is the mechanical energy conserved? No. No. What happens to it? Is it increased or decreased? Decreased. Decreased. Where does the energy go? Thermal. Thermal. That's right. And of course, it's gone. So here we have an external, non-conservative force. So neither conservation is going to apply. I guess I should keep up with my lettering here. We have two more scenarios, D and E. And I'll put them over here. This was case D. This is case E. Oh, I shouldn't have used capital letters because now capital E is like energy. So hopefully that's not too confusing. So we've run the gamut here, right? We've done a case of every single permutation here. Okay. So, what might can I pull any trickery on this one to make it a momentum conserving situation? Well, of course, I'd have to invite whatever's causing the external force and invite it in, right? So then the force of friction is internal. So let's say this is like a table, right? So let's say I'm throwing an object onto a table. Well, of course, then I just shift from one external force of friction to another, right? So now that I've made the friction of the table internal, there's going to be a force of friction on the table legs from the floor, right? So maybe I'm lucky in that the table's on some ice. That'd be fun, right? Then I could say that it's a block plus a table with an internal friction force, and then that's relatively isolated from the outside world. So then I could say the momentum of the block plus table is conserved, right? The friction is internal. Now you get very lucky if you have a table that's on ice, right? So chances are that that wouldn't work. We couldn't turn that into an inelastic collision. So probably more likely, you might say, okay, if we can't do that, we can't use momentum conservation or energy conversion. What do? Luckily, remember that our energy conservation, I'll put it over here, our energy conservation equation has the ability to handle things like that, right? So we did put in a little clause here in case we need to dump some mechanical energy into thermal or something like that. And you did have problems like that on the previous homework as well, okay? So you saw that you could work energy conservation problems if there was the KE plus PE was constant or if it was changed. So there's, if you understand what's on the board right now, you understand a very large amount of physics, okay? Are there any questions on that? Yeah?
I don't know, probably like two of them on the board.
Would I combine two of them?
Yeah, if you combine,
I don't know how you can combine them. I mean, they already are in one of these four categories. You can't, if you combine two categories, it doesn't have any meaning, right? Like if you combine this to this, how can the energy be conserved and not conserved at the same time, right? So it's going to fall into one of these four categories. Any scenario that you have can fall into one of these four. Either if the momentum is conserved or not, and the mechanical energy is conserved or not, and that's pretty much it. All of these scenarios in one way or another will appear on your homework 7 and 8. But there are no others. I've done them all for you. If you understand just this, then that's all there is, okay, to understand. Are there any other questions? Okay, so definitely get to work on this part of homework number 8. It's definitely the toughest stuff on homework number 8. Think through these scenarios of what's conserved and what's not. And in the case of momentum, of course, momentum is a vector, so it's much more annoying to wrangle. You have to do your SOHCAHTOAs and stuff. I know that students generally hate that the two-dimensional collisions because they require you to wrangle the vectors, right? Momentum. By the way, energy is not a vector, so that's always awesome. Even if you have two things colliding and they go off diagonally, if you want to check the kinetic energy at the end, it's just 1/2 mv squared. Just put in the speed of this one. 1/2 mv squared, put in the speed of this one. Does it matter that they're going off in these weird directions? Yes for momentum, no for energy. Energy doesn't care. Kinetic energy is 1/2 mv squared, v is the total speed, couldn't care less what the direction is. So energy is easy to compute. You just need to know the speed, and then you use 1/2 mv squared to find the kinetic energy. Okay. So, next we're going to move on to a topic that is somewhat unrelated. And it's going to set the template for the next couple weeks. In fact, through exam 2 and beyond. Now, here's something that you may or may not have realized. We have never once in this class addressed the size or shape of an object, right? All of the objects we've dealt with in this class thus far have been what we call point particles. So it has some mass, but it has no size, no shape. But of course in the real world that's not really true. And so what we're going to start talking about from here on forward is extended objects. They have a size and they have a shape. We'll find that many of the rules that we thought have developed in the course so far don't necessarily apply to the entire object in the way that we expect. Let me give you an example. I guess, let me put it like this. So if I have a mass m, we've learned that if you apply a net force on it to the right, it accelerates accordingly to the right with Newton's second law. F net equals ma. It's been one of the cornerstones of the class so far. You push an object to the right, it'll accelerate to the right according to how much natural resistance it has to that, which we call mass or inertia. But let me take a look at a real-world object, like so, which has some size and shape, and I'll apply that force to it. And we'll find it's not so simple. So let me try to take such an object. You can try this at home if you want. I'll put an eraser here on the table. And I'll exert a force on it to the right. Let's see what happens. Let's try it again. Well, there's really only one point of that object that actually behaved as it should have. It's a point right about here, and that accelerated. The rest of the points, some kind of spinning, right? So there is generally only one point of an extended object that actually behaves according to all of our previous laws. That point has a name. It's called the center of mass. Okay? So center of mass. It is that point on an extended object that behaves according to point particle physics. Which is all our old stuff. Another way to think of it, it's either according to point-particle physics, or another way to think of it is that point on an extended object that behaves as if all the mass of the object was there. So if you had some kind of perfect trash compactor, then you could just smash the entire object into that one point. That one point would behave no differently than it does now. Okay? So our previous laws only apply to this one point called the center of mass. That one point accelerates according to Newton's second law. That law is really only a law for the center of mass. Okay? Not all points in the object are required to follow it, just one point is. To give you another example, we talked about the fact that we throw something up in the air, it follows this arc-shaped trajectory. Let's look at a real object when I throw it into the air. Not every point did that. One point did that, right? If you look at a point on the edge, it goes like that. So this is the center of mass trajectory. So all the laws we learned before were only for one single point. So here is our goal. Our goal is, one, how do we find the center of mass? It's obviously an important point because it's the one point that we know the physics of. The second goal, of course, is what about the rest of the object? There's obviously going to be some kind of rotation involved that we need to get our heads around, and we're going to get really serious about describing rotation. Finding the center of mass is on your homework number 8. And then the rotation is actually going to take us some time. That's going to be not only homeworks 8, but homeworks 9 and 10 as well. It's the second half of homework 8, it's all of homework 9, and it's the first half of homework 10. By the way, I should mention that the cutoff for the second exam is homework 9, so the rotation unit will actually take us past the second midterm. Okay? So that's what we have to do. We'll do these in a 1-2 order. And what I'm going to start with is a little bit about how to find the center of mass. Finding the center of mass. I'm going to present to you a couple different methods, increasing in difficulty and increasing in calculation. The first one is so basic it almost seems trivial. I'm just going to call it symmetry. This is simply when there's only one unique geometric point of an object, and by process of elimination it is the one unique behavior of the center of mass. So let me show you this. So let's say, for instance, I have a solid uniform disk. Okay? Now, a solid uniform disk well, there's only one unique point of a disk that's not like any of the other ones. It's the exact midpoint, right? Halfway between my fingers right now. Okay? The one unique point. That's the center of mass. And my argument is simply, why would it be another point? If it was some point over here on the side, why that point? Why not the exact point like it on the other side, or here, or here, or here, right? So this is not like a lottery, okay? If you can identify that only one point of an object is not like all the others, that's going to have to go with the one unique behavior. So, if I throw an object up in the air, no matter how I do it, the center of mass, of course, has to go in that classic trajectory up and down. The rest of the points could rotate around it, or maybe not, but that's the one point that has to undergo our classic up and down, right? You can, any object where there's only one point that's unique, that's got to be the center of mass. A sphere, center of mass is in the middle. Solid uniform bar, center of mass is in the middle. Okay? So that's method 1. Method 2 I'll call the balance method. This is a really good method for finding the center of mass of a one-dimensional object. So the mass is really only along a single axis. Here's how it works. Let's say I have a solid bar, okay? Now obviously that has mass all along it, and it would be really annoying to have to take a little bunch of mg's for every single molecule in that thing. So what we do is we realize that the center of mass is kind of like the ambassador. If we want to take the force of gravity to pull in one spot on that object, it's there. So instead of having a bunch of little mg's everywhere, we take the entire mass of the object multiplied by g, that's the force of gravity, and where do we take it to pull? At the center of mass. It's like basically pretending that we've had some kind of perfect trash compactor, and we have literally crushed the entire mass into that point. Because remember that that point can behave no differently than if the mass is spread out. So, if I have a point particle, so I guess this pen can stand in for a point particle. If I try to hold it up by putting my hand over here, okay, good luck. Let me try it. Doesn't work. So of course, I can't put a force over here. I have to put it where the object actually is. Well, that's true as well over here. If I want to support an object by a single point, it's going to have to be the center of mass. That's the essence of the balance method. Okay? So with a single support force, and I do emphasize single, a single support force must be placed at the center of mass to balance the object. Okay? Now, that's obvious where it was going to be on a symmetric bar like that. Let me take it on an asymmetric object, something like this, where basically all the mass lies along a single axis, more or less, but it's not symmetric. So I try it here, and whoops, that doesn't work. If I go over here, right about here, I find that it balances. And so what I've concluded is that the center of mass of this object is here. Okay? And notice, by the way, since the mass is not symmetric, right, there's more mass over here, the center of mass is pulled, it's not in the midpoint of this bar, it is actually pulled toward the side where there's more mass. So that's an important point. I'll write this down and we'll pick it up next time. If you have asymmetric mass, you'll find that the center of mass is skewed towards the larger mass end. So it's not at the midpoint, or as we sometimes call it, the fancy, the geometric center. The center of mass can be pulled significantly towards the end of the object if there is more mass there. Okay, we'll pick up there next time.